Hey there, awesome physics students. Let's talk about springs and the forces needed to stretch or compress springs. Now, first of all, why do we care so much about springs? Well, they're not so interesting all by themselves. It's because springs behave as toy models. That is, many other materials will, when you bend them, stretch them, or compress them, they will behave like springs in the way that they will try to go back to their equilibrium position. So we can use springs as a toy model. That is, springs are a simplified picture that we can easily visualize and understand what's going on with the springs, and then we can transfer that understanding to other objects that behave like springs. Okay, so let's talk about what are the forces acting on springs or how they behave. So imagine you have a spring attached to a wall here. Let's put the origin for the horizontal coordinate x right there. So this is the point where the spring is totally relaxed. It's not exerting any force on anything. And imagine that I try to stretch that. So this is a positive displacement I'm putting on the spring. Well, the spring is going to resist that and try to go back to its equilibrium position. And so the force the spring is going to exert is going to point in the opposite direction as the displacement. Similarly, if I try to compress the spring and I put a displacement on it in the negative x direction, then the spring is going to push back the other direction, trying again to get back to its equilibrium position. So again, the displacement and the force are going to be opposite. And this is why we call this point the equilibrium point. The spring is always trying to get back to that equilibrium point, or we say the spring is a restoring force, trying to restore the position back to the equilibrium point. If we think about the directions of these two, the force is going to be in an opposite direction to the displacement. So if we write down the force compared to the displacement, there's going to be this negative sign in between them. And because of the way the spring behaves, there's a spring constant here that tells you about the stiffness of the spring. And this is going to be the force is going to be in newtons. The displacement is going to be in meters. So the spring constant is going to have units of newtons per meter. So that the meters will cancel here and you'll get newtons on this side. Okay, so how does this spring law, or the spring force law, which is called Hooke's law, how does that behave on a graph? Or how can we visualize that? So let's plot the force versus the displacement. And again, this is in one dimension. Let's just think about the magnitudes of the forces right now. So for a second, forget about this negative sign. The idea with this graph here is that if you stretch it just a little bit, the force is going to increase a little bit. And if you stretch it a little bit more, the force is going to get a little bit more. And if you continue to stretch it, the force is going to continue to increase. And that is what this equation is telling us, is that it looks like a traditional line, y equals mx plus b. In this case, b is 0. There's no y-intercept. And y, that is the vertical axis, the force, is the slope times the horizontal coordinate, which is x actually in both cases here. And so this slope here, as you can see from this equation, the slope is going to be equal to the k, the spring constant. And again, that k tells you how stiff or how difficult to stretch or compress is that spring. How stiff is it? And that is going to be characterized in units of newtons per meter. Okay. The key thing to remember here is that this is a linear relationship. If you double the stretch, that's going to double the force that the spring will put down, and that depends on the exact slope of that depends on the stiffness of the spring. So different springs will have different slopes here.